Hi everyone. Welcome to the correction video to Bode plots by hand, complex poles, or zeros. This video replaces the last half of the Bode plot video starting at 6 minutes and 40 seconds. I made too many errors at the end of that video to correct with pop-ups and annotations, so I thought this would be a better way to clear up the confusion. If you got to this video through a search and have not yet watched the previous video, you can click here. But let's get back to where we left off. I had just written that the real and imaginary components of a second-order transfer function with complex poles are as follows. This is after we substituted s equals j omega in the transfer function. So now I want to walk through the straight line approximation of the Bode plot. Keep in mind as I present this that when you approximate a Bode plot in the future, you won't actually be going through all of this math. Instead, you'll take the rules of thumb that we develop here and apply them directly. Now, I want to present this math to you here so you can see how we got to those rules of thumb. I'll explain as we go along. We'll start by drawing our empty Bode diagrams, one for gain and one for phase, and then I'll mark in the middle somewhere where our break frequency omega naught is. And now we can visualize how the total plot will look by dividing it up into three different sections. The first section is where your input frequency omega is smaller than your break frequency omega naught. Then the second section is where your input is higher than your break frequency. And lastly, the third section is where your input is exactly equal to your break frequency. Let's start with the first case, where the input frequency omega is much smaller than the break frequency omega naught. I'll copy the real and imaginary components again here for reference. Now in this case, omega over omega naught can be approximated as 0 since it is a small number divided by a large number. For the real component, the numerator becomes 1 minus 0 squared, or just 1, and the denominator becomes 1 plus 0 squared, and this just reduces to 1. Now the imaginary component becomes very small number divided by 1, which is a very small number, so small that we can approximate it as 0. It might be pretty easy to see at this point what the phase and gain are, but just in case, let me show you two different ways to determine it. The first way is to solve it mathematically. We know that the gain is the magnitude of h of j omega, and this is pretty easy to show that it just reduces to 1. And then we can convert this into decibels by taking the log base 10 of 1 and multiplying it by 20, which becomes 0 decibels. And we know that the phase is the argument of h of j omega, which is the arctangent of the imaginary component over the real component, which is 0 degrees. The second way of thinking of this is by plotting this point on a real imaginary axis and seeing graphically what the phase and gain are. In this case, the gain is the distance between the origin and the point, which is 1, and the phase is the angle off the positive real axis, or 0 degrees, just like we calculated. So now we can draw this approximation on our Bode plot up to the break frequency. That's 0 decibels for gain and 0 degrees for phase. I know you might be thinking that this is only accurate when the input frequency is much lower than the break frequency and not up to the break frequency like I've just drawn. But remember that this is a straight line approximation only, and it's intended to give you a rough idea of the shape of the plot and not give you exact values. So let's move on to the second case, and that's when the input frequency omega is much larger than the break frequency omega naught. Now omega over omega naught dominates the equation since it's a large number divided by a small number. And the numerator of the real component becomes negative omega over omega naught squared, since 1 minus a really large number is approximately the negative of that really large number. And following that logic, the denominator becomes this. But this second term in the denominator is much smaller than the first term because it's only squared, whereas the first term is raised to the power of 4. Therefore, as omega over omega naught gets larger and larger, the second term becomes less and less important and can be ignored. After cancellation, the real component just becomes negative omega divided by omega naught raised to the negative 2 power. And we can do the exact same thing to the imaginary component and get negative 2 zeta times omega over omega naught raised to the minus 3 power. Again, we can solve for the magnitude of h of j omega and get this really large square root. Luckily, we can simplify this by noting that the second term becomes really small in comparison to the first term, since it's raised to a negative 6 power versus a negative 4 power. and that makes the gain equal to omega divided by omega naught raised to the minus 2. But how can we interpret this in decibels? Well, remember that to get decibels we use 20 times the log base 10 of the gain, and using a property of logarithms we can move the exponent outside as a multiplier. And so it becomes minus 40 times the log base 10 of omega over omega naught. At this point I find it easier just to plot a few points and see the trend. So I'll mark a few frequencies starting at omega naught. Remember, this is a log scale. If the input frequency omega equals omega naught, then when you divide them you get 1 and the gain just becomes 0 decibels. And I'm going to mark that on the graph. When omega is 10 times larger than omega naught, the gain becomes minus 40 decibels. And when it's 100 times larger, the gain becomes minus 80 decibels. And I think you can start to see a pattern. The gain falls off at a rate of minus 40 decibels per decade when omega is much larger than the break frequency. So now on to phase. The phase is the arctangent of the imaginary component divided by the real component. And if we cancel terms and simplify, we get the arctangent of 2 zeta divided by omega over omega naught. And this approaches 0 degrees as omega gets larger and larger compared to omega naught. But is 0 degrees the right answer? Well, no, it isn't. Remember, both the real and imaginary components are negative. Therefore, on a real imaginary plane, you'd expect the point to lie somewhere in this quadrant. And since the imaginary component goes to 0 faster than the real component as omega over omega naught gets larger, we'd expect the point to converge on the origin from the direction of the negative real line. And the argument of this point is minus 180 degrees, not 0 degrees. So where did we go wrong? Well, the problem is that the function arctangent doesn't keep track of which quadrant you're in, and so the negatives cancel each other out and we're left with an incorrect angle. So you need to keep track of the signs yourself or use the function arctangent 2, which will keep track of the signs for you. So let's plot this up above. For the gain we have a straight line with a slope of minus 40 decibels per decade. And for phase we can approximate it as minus 180 degrees. Alright, that just leaves what happens when your input frequency equals your break frequency. In this case, omega divided by omega naught equals 1, which zeroes out the numerator in the real component and makes it a value of 0. The imaginary component becomes minus 2 zeta divided by 0 plus 2 zeta squared, or minus 1 divided by 2 zeta. Again, we solve for gain in the usual manner and get 1 divided by 2 zeta. If we convert this to decibels, we get minus 20 times the log base 10 of 2 times zeta. At this point you should note that if zeta equals 0.5, then we take the log base 10 of 1, which makes it 0 decibels, or no peak at all. If you have more damping than 0.5, then the peak actually goes slightly negative or down. And we usually don't estimate this negative peak when approximating a Bode plot by hand, but it's nice to understand exactly what the plot is doing. And finally, if you have less damping than 0.5, then there is a peak at the break frequency of minus 20 times the log base 10 of 2 zeta. And if you have no damping at all, then the peak jumps up to infinity. For phase, we take the arctangent of infinity and find that the phase is minus 90 degrees. Remember, I took care of the quadrant for us. And now we can plot this on our Bode plot. The gain plot has a peak at the break frequency if the damping ratio is less than 0.5. And the phase at the break frequency is minus 90 degrees. But the slope between 0 degrees phase and minus 180 degrees phase changes as a function of zeta. Now you can either look up the shape of the graph in a chart based on your zeta, or you can just approximate it directly by drawing a line starting at omega naught divided by 5 raised to the power of zeta to omega naught times 5 raised to the power of zeta. Now, I personally don't use this rule of thumb because more often than not, I'm going to plot a Bode plot using a tool like MATLAB. But this is still nice to know because when I'm designing a filter in the frequency domain, I can visualize that by decreasing the damping ratio, I'm making a faster transition between 0 degrees and minus 180 degrees phase, and it's useful to know that. These three lines are just an approximation of the Bode plot, and can help you understand the shape of the frequency response for your system. In general, the exact shape would be smoother, and follow more closely to the thick yellow line that I'm drawing on top here. The last thing I want to mention is that just like we did in the previous videos, a 0 is just a 1 divided by a pole, or it's the negative of the pole if you're plotting it on a log-log scale, like a Bode plot. So the frequency response of a pair of complex zeros is just the reflection about the horizontal axis of the response of a pair of complex poles, just like I'm drawing with these red lines, and I think that's pretty neat. Now, I hope this correction video cleared up some of your confusion I might have caused from my previous video, but if you still have questions or comments, please leave them below. And once again, thanks for watching.